Hello everyone and welcome to a new episode of All Things IDA. In this episode, I'm going to be covering how to generate disassembly lines and how to work with instruction decoding and what's the difference between the two aspects. Let's get started. Now, if we look at the regular disassembly window, what we see here is the colored lines of the disassembly lines. So these are already disassembly lines. We can programmatically retrieve the disassembly lines by simply using the generate disassembly line helper method inside IDC. So let's take a quick look. If you go to IDC, we have a bunch of methods. One of them is get disassembly. This one eventually calls generate disassembly line and it goes to IDA lines. So in reality, if you recall from last time when we covered all the header files, allins.hpp is responsible for working with lines and in particular disassembly lines. So we can actually directly go to IDAPI.generate disassembly line or simply through IDC. So depends what we want, idc.getDisassemble or directly call it. So let's start with IDC, which is the same behind the scenes. So if I'm here and I type idc.getDisassemble line, idc.here for the current selected address, and I press enter, I should see call EBX and the whole thing as per the generated disassembly line. Same if I put the cursor here, repeat the same instruction, I get the same thing. Similarly, I could directly call it inside IDA API or IDA line. So IDA API.generate disassemble line. Now, here we notice the C++ prototype takes the output string as a first argument. In IDAPython, output argument, the first argument here, if it happens to be a string, string pointer, get mapped to a return variable, return value. So if I put here in IDAPython CLI question mark function name, I get a quick help. And so here we can tell generate disassembly line does return the string, takes EA and flags. So while we are looking at the actual C++ reference, the IDAPython version differed slightly. So here at API, generate disassembly line, idc.here, and the flags. What can we use for flags? For example, we can pass remove tags or generate multi lines and so on. If I don't specify that flags and specify flag 0, I will get colored lines. So this is already multicolor line. We have the push is in a different color, the number is a different color, and so on. So here, generate assembly line with flag 0, it will return a tagged line or a colored line. So here we see the color codes, the instruction, and so on. What we can do, we can then tag remove. So if we say s equals this line, and IDAPI.tag remove, we remove the colors. So we get non-colored disassembly line. So generate disassembly line or idc.getDisassemble will let us just go through the processor module, disassembles, the output part will render that disassembly, whatever it is, and then return it as a string. So it's a long pass actually, it's a bit not performant. Now, the advantage of generate disassembly lines is what you see in IDA view is what you get. So for example, if this was undefined and we say get disassembly line here, we get exactly what we are seeing, like db5f and so on. So if we go to data, let's say this is a line and we say generate assembly line, we get data, db, etc. If it was a d word, for example, this one, we'll get dd and so on. So this is for generating this assembly line. Now I've seen some people do some trick in order to access the operands. They first say, all right, I'm going to get the disassembly line into a variable. Then I'm gonna say, I'm gonna split it by space. And now they think they have the individual components, let's say to access the operands. This is not optimal. There are different ways we can deal with that. So for example, if we want to just get the instruction name, the mnemonic, we have idc.print instruction mnemonic. I will give it an address. So here, and gives me directly the instruction name. And we have another one to retrieve the mnemonic, the operand. So print operand, we give it the address and the operand number. So here, if we want to get this operand, we can just simply say idc.print operand. We give it the address and we give it operand 0. We got that operand. So this is okay, but you will see next there's a better way to get the operand and the mnemonics. So that's generating disassembly lines. So now let's talk about instruction decoding. Instruction decoding is related to the decode underscore instruction function. And then you will see there are other helpers. If we want to look at the helpers first, we have the first helper is in IDAUtils. It's called IDAUtils.decode instruction. Decode instruction in reality behind the scenes really called the ua.hpp is decode underscore instruction. So if we go to ua.hpp and we look for decode instruction, it says, hey, a decoded instruction, if you give me an output instruction structure and the address. If you give me the address, I will populate an instruction T. So what's an instruction T? So if we look at the instruction T, is what holds an instruction. An instance of an instruction T will hold the code segment, instruction pointer, and effective address. Most of our programs we're dealing with use flat memory models, so CSIP will be the same as the linear address EA. So we rarely have to look at CSIP, except maybe if we're dealing with, say, DOS programs or other segmented programs. So EA is the EA of the instructions. IType is the instruction number. This is what will let us tell what instruction it is. So the IType is just a number. It is coming from allins.hpp from the SDK. So allins. Here in allins, we have an n underscore. The nn is for the PC processor module. So if we're working with the PC target, we can then decode instruction, check the IType against nn underscore. For example, if we're working with ARM, we can decode instruction, check against ARM underscore. So we have ARM underscore, and so on. So the IType, once we decode, check the IType, we can check if it's a call, if it's a move, and so on. We can get the instruction size, and we can also get a maximum of 8 operands. Each operand is of type operand T. That describes what's an operand. Then for other helper methods and so on for an instruction. Let's take a look at an operand. What makes an operand? Operand has a number, type. This is very important. What is the type of the operand? What are we dealing with? Are we dealing with no operand? IDA instruction doesn't have a field called count of instructions. Instead, it just have an array of top 8 operands. And if the instruction has 2 operands, then it will terminate with an operand of type O void. So it will have operand 0, operand 1, and operand 2 will be O void type. So every register can have a type. It could be an operand that is a register, or it could be an operand that's a memory reference, or a phrase, or a displacement. An immediate, just an operand that is a number, immediate number, or a far address, or a near address, or something custom that you as a processor module can use those reserved fields to your whatever suits your need as you decode and transition from decoding to outputting instructions to analysis throughout your internals of the processor module. But these are most common. These will make more sense, those operand types. So after we go over the operand type, we select on the operand type, what's the operand type register, and so on. And then based on that, we access its field. So if the operand type is reg o underscore reg, then we can access operand.reg to get the register number. And those register numbers, when we design a processor module, we also make an enum corresponding to register numbers and their symbolic names. Then we can also, if the operand type is of type O immediate, we can then access operand.value. If the operand type is memory or displacement, or a near or a far address, we can access operand.address. In addition to the operand type and its different fields, value, register number, and so on, it also has a D type, data type. D type is for the type. How big is the type of that operand? So is it a byte, word, D word, and so on. So this is for the operand. Its type is data type, and its corresponding value fields: .reg, .value, .address, .phrase, and so on. So now if we go back and for a second switch to IDC and show you a trick. So IDC also supports instruction decoding. But we're gonna leverage the output to show you the whole decoded instruction. So I'm gonna position the cursor here and say in the IDC prompt, decode instruction, and give it an address. So type here and enter. And here we have the output of the instruction object that has been dumped. So decode instruction returns an instruction object, and in IDC we can simply pretty print an object. So here we have test takes two operands. This is instruction operand 0. We'll look at it. Operand 1. And also aliases, operand 0, operand 1, in case you're accessing it through an array, subscripts, or all those fields. And these are the actual instruction fields. So here itype we have is nn underscore test is 210. We can double check. IDA, so it's not accessible in IDC, unfortunately. So IDAPI.nn, and here test. It should be 210. We also have in IDC, we get the mnemonic string and so on, and the instruction size. And here, let's look at the first operand, CL, operand 0. First, we don't know what to read from it. First, we have to check its type. So it says type 1. Type 1, which means O underscore register. Great. Now we can look at the reg field. So now you can see reg is 17. 17 should basically denote CL one way or another. How do we figure out what it means? This is also something coming similar to allins.hpp. When you're writing a processor module, you would have defined the special enum containing the name of the register and their numeric values. Luckily for the PC processor module, we do have such mapping inside the SDK in intel.hpp. If I go to intel.hpp, this comes from the PC processor module source code. We have the register numbers. So here we said test CL, we saw it's 17. So can we really map this to CL? So here CX is 1, here 15, 16, 17. So this is where we could map what is CL. Let's do one more decoding. Let's decode the move here and just show you as well from IDC. So just decode instruction here. I won't put the semicolon. If I put the semicolon, it's treated as a statement, not as an expression, and it won't display the return value. So here, if I just put semicolon, nothing happens. So just keep it as an expression. And let's also manually inspect this. So here we should expect to have nn underscore move. So let's open all ins and look for nn move. And here, among all the instructions, we have so many forms of move, but in particular, we have that instruction move, nn move. If we have move zx with sign extensions, that's a different instruction. So nn move is what we want. We can check its value as well, IDAPython move in decimal form. So it's 122. Let's check here the I type, indeed, 122. Register, so OP0 should be of type OREG. So here, OREG, the type of that operand 0, type is 1, which is register. Therefore, we can access the register field. So that's the register field, 7. Let's double check if 7 really means EDI. Indeed. But I'll show you a better way how to actually work with this. And for this second operand, we should assume that the second operand, which is OP1, of type O underscore mem. OMEM, let's see what's OMEM. OMEM should be operand type 2. So let's scroll here. So operand type, second operand, type 2, which is OMEM. Because it's OMEM, we can access the value, which actually we can see the value encoded here. 53, 30, 84. That's the address of that name. But we will see it in the decoded instructions. So the type is OMEM. And to access the actual memory, we say is operand.address. So the dot address, this is the address, and this is the actual address, which is this one, 53, 30, 84. It's already encoded as well for us. And that's how we interpreted it manually. So we used the trick in IDC to quickly dump the decoded instruction. Now, how would you do it in Python? So suppose in Python we're looking for, let's say, here we have a series of push. I'm gonna show you a small loop where I'm going to look for pushes and display the values here that have been pushed. That's all I care about. So Shift F2, snippet window. Let's create a new snippet window. And I'm gonna start my enumeration by the current screen address. So here EA equal, let's say, add API get screen EA, which is equivalent to IDC.here. Now we're gonna loop indefinitely. I'm gonna import IDAutils, import IDC, import IDAPI. And that's mainly what you really need. You don't need to import anything like IDA underscore and a module name. Once you import IDAPI, you have everything. Now let's decode. So instruction dot, remember, we are gonna use IDAutils dot decode instruction. So IDAutils dot decode instruction. We give it an EA, if not instruction, or let's break it. Let's keep. So if not instruction, basically cannot decode. We could not disassemble. Great. Now I only want push instructions. So here we can filter if instruction dot I type not equals IDAPI dot and then push. Continue. Only accept the push, basically. Now we know that we are looking for pushes. Now we want to push immediate. We don't want push registers. So we can also filter. If instruction of 0, this is the first operand, dot type is not immediate, that's the type. If it's not an immediate, also I don't want it. Now, as I said, of course, we can combine all the conditions together. So here, not an immediate push. Finally, now we know it's an immediate push. We can access, to get the immediate value, we can access operand.value. So here now we can say print push pushed instruction of 0.value as hexadecimal. And we break when we stop decoding. Let's break when we don't find a push. So if I started from here, it will break when we arrive to the call. Like this, it won't go indefinitely. So that's good. One more missing piece is how do we advance? So we started with EA, which is the current screen address. So let's put it here. And to advance, so each time we decode successfully, I will directly advance EA plus equal instruction dot size, because the instruction, if it's decoded successfully, we have the size. So I'm simply skipping to the next instruction. Now, position the cursor here. It will run stop at the call. Let's see what will happen. So Alt R, and we got here all those pushes. By following this kind of logic where we decode an instruction, we check the I type correctly, we check the type of the operand, and then we check the proper field in the operand, we can do really anything like writing an emulator or an intelligent code lookup plugin or anything you like. And I would like to give you one more example now, since I mentioned it, about registers. So I told you we can look at the register definition in intel.hpp, for example, to try to gauge what register we're dealing with. If we're working in C++, we could include intel.hpp, and then we can say if operand 0.reg equals r underscore ax. Here in IDAPython, if we try to say IDAPI.r underscore ax, it's not there because we don't even have, let's say, IDA Let's duplicate that snippet. So let's clone it. And now change it in such a way that we are only interested in instructions that take a single operand that are EDI, for example. We're just looking for EDI. How do we compare if we're dealing with EDI? So here we don't need all those. All right. So here, so let's decode the instruction. If we can decode it, we're gonna check if it's EDI. So there's a trick for that. First, we decoded it. Let's say now, if the instruction 0 is idautils.procregs.edi. So that's the magic I want to share with you. We have a helper class called procregs, which will take whatever you type here and use some internal APIs to resolve a register by name. And then it will also try to match the register's size. So it will match a register by name and also gets its D type. Now, when we type that expression here, if instruction of 0 equals this, we have overloaded the equals operator to check for both the register number and the type. So let me see if I can find it real quick here. So here's the magic between procreg and IDAutils. Behind the scenes, it uses regd type, which describes the register number and the d type, and that's the overloaded equal. And so using this trick, if instruction of 0 equals this will check if it's exactly RDI. So now putting the cursor here, running it, here it tells us found EDI exactly EDI. We didn't have to hard code any register number. So if I wanted to check this differently, I would have said instruction of 0 dot reg equals, and we'll have to figure out what's RDI. It's 7, so we'll have to say 7 and run it. But our code, this code here, will work for EDI exactly. This code here will work for DI, or basically here it's RDI, that's it, and RDL. So we only have two regs. So RDI, if we check for 7, we're gonna match for DI, EDI, RDI. That's the 7. But if we check with procregs.edi, we're really checking for reg equals 7 and dtype equal dt dword, for example. So that's the advantage of using procregs. And it will work with ARM. So if you were in ARM, you could have said like R0, for example. It would have worked equally without having to guess what is R0. Now, if you want to build that knowledge base, you would probably use the IDC version to dump the instruction and start to build the numeric values and what they mean. So let's say I don't know what's the I type for an add instruction. It's easy. So as long as I can decode instruction and look at the I type, 6, I deduce that 6 is add. That's it. And so you can reverse build it. So here, ESP, I could have guessed ESP as well from operand 0. The type of the operand is oreg1 and 4, which is r underscore sp as well. We can 4 and this one. All right, so that's it for today. We covered the difference between generating disassembly lines and proper instruction decoding. We covered what's the I type and what are register numbers and operand types, operand sizes, and how we can use procregs shortcut from IDAUtils to distinguish between different registers. I hope this was useful. This will not be the last time we work with instruction decoding. If you have questions, please leave them down below in the comment section. Thank you very much.